Hopefully this will be a short video discussing when to use the words electrophile and nucleophile. So an electrophile is an acceptor of a pair of electrons, and it comes from this idea that the phile, lover of electrons, negative charged things or partially negative charged things are can be electrophiles, but the definition we need to be aware of is that they will accept a pair of electrons in a mechanism. And nucleophiles will donate a pair of electrons in the mechanism. There is a relationship there between this perhaps behaving like a Lewis base and the Lewis acid. Lewis acids can accept pairs of electrons. So it's a similar sort of idea, but in these mechanisms, let's think about what we mean. So I've done whole videos on SN1 and SN2. I'm not going to do the whole thing again now, but in a general reaction for a nucleophilic nucleophilic substitution, SN1 or SN2, you will have a halogenoalkane, say, and that bond will be polar. And for example, in the SN2 reaction, we've got a nucleophile like a hydroxide attacking that delta positive carbon. So this is nucleophilic substitution, because the thing that's attacking our functional group, our molecule, our organic molecule that we're interested in, this is acting as a nucleophile because it's pushing or donating a pair of electrons to that carbon, which is causing that bond to break. So we end up forming the methanol product and chlorides, so CH3OH and chloride. So this is behaving as the nucleophile, the reagent we're adding, the thing we're adding to our organic molecule. And you can make the same sort of argument for benzene ring reacting with an electrophile. So again, this is our organic molecule of interest. It's being attacked by an electrophile. So here, the benzene ring, in particular the electrons in the delocalized system, are behaving like a nucleophile, but they're attacking an electrophile. So you always have one, you can't have one without the other. This is behaving as a nucleophile, this is accepting the pair of electrons, but this is our molecule of interest. This is the thing that's doing the attacking. This is the thing that's doing the attacking. And then the last example is when you've got a reaction, say, between an alkene, I'll just draw ethene, and an electrophile. So I'll use HCl as an example. HCl being a polar molecule because chlorine is more electronegative than hydrogen, and this delta positive end, this thing is attacking our organic molecule of interest. And so this thing is behaving, or this bit of the molecule in particular is behaving like an electrophile, and you end up with something like this, plus a chloride ion. Now this second stage, of course, the chloride then attacks the carbocation, but it's this reagent here that's behaving as the electrophile. So this is doing electrophilic addition to an alkene, and that's always going to be the case, even though the chloride here is behaving as a nucleophile. All right. This feels like it's not going to be picked out in detail, but nevertheless I'll cover it. So what goes on when you've got a non-polar electrophile reacting with the alkene? And in that situation we've got a non-polar molecule, but this double bond is a sigma bond and a pi bond. The pi bond is a pair of electrons that's spread out above and below the line, if you like, between the two carbons, and it's full of electron density. So as a chlorine molecule is moving in the solution or moving in the mixture past an alkene, it might be that the electrons in that pi cloud push away or repel ever so slightly the electrons in this bond, just pushing them away a touch. That makes this, so it's an induced dipole essentially that's going on there. And so we end up with a delta negative, delta positive on that chlorine molecule. It'll be very small, but enough to allow that pi bond, one of those two of the double bond, attack that chlorine, causing that one to break. So this is exactly the same as up here. It's just that instead of an H being added, it's a chlorine being added. So you'd have chlorine in that place, and you're getting dichlorination of the alkenes. You can see that. So this, instead of having a hydrogen from there going to there, you'd have a chlorine from there going to there, and you end up, might as well draw it, you end up with that as the carbocation intermediate and a chloride, which then subsequently attacks. So again, that chloride in this part of the reaction is behaving as a nucleophile, but it's still electrophilic addition, because that's our organic molecule of interest. That's the thing that's being attacked by.